Let's look at an example. So here we want to consider the same RC phase shift oscillator that we saw in the previous video. And in this case, we're told that we have an R value equal to 1K and a capacitance equal to 0.1 microfarad. And so what we want to find is two things. We want to find the oscillation frequency in hertz, and we want to find the minimum R2 value that's going to result in oscillation. So again, here's the circuit copied from our previous video. We have our 3 RC stages with buffers in between them so that we don't have loading effects on the state of different RC stages on the other stages. And then our final stage, our A3, is our inverting amplifier. So what we had found in our previous video is that our resonant frequency, omega naught, was equal to 1 over root 3 RC. So of course we're going to use this equation if we want to find our oscillation frequency. The main difference though is here we were asked to find the oscillation frequency in hertz. So we just have to remember that our omega in general is equal to 2 pi f. So turning that around, we can have just of course say f is equal to omega divided by 2 pi. So we have to introduce a factor of 1 over 2 pi into this equation. So we can say f naught is equal to 1 divided by, add our 2 pi in the denominator, and then we have root 3 RC. So then plugging in our values, we have the 1K ohm, so we can put 1,000, and 0.1 microfarad, so micro times 10 to the minus 6. So we get something like this. Plugging this value in, we get that this is approximately 919 hertz. So this would be our answer to the first part of the question, which is what is our frequency of oscillation? So we had also found in our previous video that for oscillation to occur, that this ratio of R2 over R has to be greater than or equal to 8. And so remember, all of these values are our R values, part of our RC networks, and then we have this R2 value up here, which is part of our inverting amplifier configuration. So of course, if this R2 over R is greater than or equal to 8, and our R is just 1K, what that means then is our R2 has to be greater than or equal to 8K ohms in order for oscillation to occur. And so to answer the question specifically, the minimum R2 to result in oscillation would be 8K ohms. So one thing to ask ourselves then is, if we're building an oscillator based on this configuration, how do we adjust this frequency of oscillation? Maybe we want a frequency of oscillation closer to 1K hertz, or not 1K hertz, we're basically there. Let's say we want it closer to 10K hertz, so how could we change that? So looking at this omega naught equation, we see we basically have sort of two knobs to adjust we can think of. We can adjust this R value, or we could adjust our C value. So for instance, if we decrease our C value, we're going to be increasing our frequency. So we had not necessarily a large capacitance, but we could definitely make that smaller pretty easily, and we could increase our oscillation frequency. One thing to keep in mind, if we're adjusting our R value, that's going to require us to adjust, or at the very least keep in mind, our R2 value to make sure this ratio of R2 over R1 remains greater than 8. So what I want to do now is take a closer look at the contribution from each of these 3 RC networks, just to kind of reinforce what we had seen in the previous video. So we want to consider our contribution of each RC network at that oscillation frequency. So each RC network at our frequency equals omega naught. And so what we had seen previously is that sort of our transfer function, we can think about it for our RC network, is J omega naught RC divided by 1 plus J omega naught RC. And so basically we're just plugging in our equation for our omega naught. So as we set up here, omega naught is equal to 1 over root 3 times RC. So the RC terms are going to cancel out in both of these expressions, and we're going to be left with j times 1 over root 3 in the numerator, and 1 plus j times 1 over root 3 in the denominator. And so we can multiply by root 3 in the numerator and the denominator to clean that up a bit. So we get j over root 3 plus j. Okay, so now let's change this to polar form. So we want it in terms of a magnitude and phase. So the magnitude of our numerator, so we can essentially write this as 1 angle 90 degrees. And so remember our j, we can think about what that looks like in our complex plane. If we have our real and imaginary, so if we have j, we're just at a point here. So of course that's going to make this angle 90 degrees. So now for our denominator, for our magnitude, we're going to have the square root of a squared, so square root of 3 squared is 3, plus 1 squared, which is just 1, angle with the inverse tangent of 1 divided by root 3. So now we can divide our magnitudes to get our overall magnitude, which is going to be 1 over root 4. And we subtract our phase angles, so 90 degrees minus the phase angle in our denominator. So we have 90 degrees minus 30 degrees, which is what that inverse tangent comes out as. And we see that this can be reduced to, of course, 1/2 angle with 60 degrees. So what we see is, as expected, each of our 3 RC networks is contributing a 60-degree phase shift. So each RC network is giving a 60-degree phase shift. So then the 3 RC networks are giving us a total of 180-degree phase shift. And so remember, we also have this inverting amplifier, which was giving us a 180-degree phase shift. So then if we consider these two together, what we have is a 360-degree phase shift. And so this for our loop gain then means that we're in that case of having some n times through 60, where n is 0, 1, 2, 3, and so on, in order to get our oscillation. Another thing that we can note is that each of these RC networks attenuates the signal by 1/2. So each RC network attenuates the signal. And so we see that attenuation is represented by this 1/2 here. So it's basically reducing the magnitude by 2. And so of course what we see is if we have 3 of them, we have 1/2 cubed, which is just 1/8. And so this is of course where that ratio of R2 over R comes from, being greater than 8. And essentially what we can say is that this inverting amplifier is having to overcome this decrease introduced by our 3 RC networks. So if we're able to overcome that, then we see oscillation. If not, then we won't.